Hello everyone, I am Daksh Thapar, a PhD student at Indian Institute of Technology, Mandi. I'm glad to present a collaborative work on behalf of our team at AIMS, IIT Delhi and IIT Mandi on a new framework for enhanced segmentation of surgical instruments. Segmentation of instruments is essential for many technology-driven minimal invasive surgery applications. Semantic segmentation treats multiple objects within a single category as one identity, whereas instance segmentation identifies individual objects within a category. Instance level mask is needed for specific tool tracking, activity recognition, and skill evaluation. The major challenges include type of surgery, similar looking instruments, dataset size, imbalance in tool statistics, and challenging conditions during surgery. The research on surgical instrument segmentation is largely driven by EndoVis2017 MICI challenge. It consists of a robotic minimal invasive laparoscopic dataset with 7 instruments type which are thin, long, and tube-like. State-of-the-art isocyanide fine-tunes mask and backbone and achieves an IUU of 0.55. TR uses a transformer architecture that exploits tracking cues and gives an IUU of 0.6. We found that even though these methods give a reasonable output for bounding box and mask, but misclassifies the object. Just changing the predicted class label with the ground truth label gave an average precision boost from 0.65 to 0.9, showing the misclassification. The contribution of this work includes a new classification framework. Due to a significant difference in appearance of the natural objects and medical instruments, we had a carefully designed classification module as the new stage to the existing techniques. The instrument's aspect ratio and oblique appearance brings background, so we propose using mask-based attention rather than bounding box-based one. Surgical instruments show similar appearance, and hence we separate the representation learning and classification stages using arc loss followed by cross-entropy loss. Here is our architecture that shows how we add a third stage to existing mask-card CNN backbone. It is not limited to mask-card CNN but can be replaced by any two-stage backbone that provides us with masks. We update or correct the class predictions of a mask from the previous stage. During training, we use ground truth mask, and while testing, we use masks predicted by the second stage. We perform hard attention on multiple skills of the features of the image. It is effective for training small datasets as we separate the learning of feature representation and classification. We perform metric learning using arc loss followed by categorical cross-entropy loss. Here are our results on our EndoVis2017 dataset, where it significantly outperforms the existing fine-tuned natural image segmentation methods as well as EndoVis-specific methods by huge margin. We had a third stage classifier module with different backbone architectures, mask-card CNN, and transform-based mask-to-former, and show that our solution is applicable to different architectures. We also show the generalization of our methods on another dataset, that is EndoVis2018. We perform different ablation studies to show the effectiveness of our claims. While comparing it with existing methods, we perform well on sparse classes like Chasmai retractor and on highly overlapping classes like ultrasound probe. A misclassification happens when the tool appearance drastically changes due to change in tool tip or orientation. So to conclude, in the current study, we investigated the reason for low performance of SOTA vision methods on surgical instrument segmentation. We identified that the classification is the bottleneck for such methods, and carefully designed architecture innovations are proposed to mitigate the challenge. We also conduct exhaustive experimentation on EndoVis2017 and 18 datasets, comparing a large number of instance segmentation methods and ensure that the methods generalize well. Thank you all.